All right. So in this tutorial, we're just going to go over organic chemistry. So what is organic chemistry about? What do we get to look at under organic chemistry? So organic chemistry basically we're looking at study of carbon containing compounds. So as we get to look at the carbon containing compounds, we're interested in the structure of these compounds. We're interested in the properties. We're interested in the composition. We're interested in their reactions and also how we get to prepare these compounds. For example, how do you get to draw or present a structure of maybe, let's say, an alcohol? So you get to see that there are different ways in which you can do that. Okay? But before we get into all that, we basically have to understand the carbon that you're talking about. So what is all about carbon? So we're going to find that organic chemistry is going to deal with carbon containing compounds, of which most of them are going to be made up of carbon and hydrogen. So most of the compounds that we're going to talk about are going to have carbon and hydrogen. But in some cases, we may see some nitrogen containing compounds, oxygen, halogens, of course, phosphorus, silicon, and sulfur. So we'll get to see that. So let's get into this now. So what do we know about carbon? So what we need to understand, the major things that we need to understand about carbon is the fact that carbon basically gets to form billions of compounds. Okay, so how is that made possible? So carbon is a very interesting element, which is basically has got a valence of 4, implying that it has got 4 electrons in the outermost shell. Okay, so 4 electrons, so it has got a valence of 4 electrons in the outermost shell. So the fact that it has got 4 electrons in the outermost shell, it is able to form different forms of hybridization. It undergoes different forms of hybridization, of which we have the sp, the sp2, the sp3 hybridization. So these are the hybridizations that carbon gets to undergo. So let me try to give you some examples. What about if you get to talk about sp3? So an example is if you get to talk about methane, you're going to see that basically you're going to have 4 bonds to hydrogen, right? So that is one way, implying that the carbon is going to share an electron in each bond. So there's an electron of carbon in each bond, which are 4. And hydrogen will also come with its own what? With its own electron. So each hydrogen atom will come with its own electron. So the basic idea is every bond that is formed should have 2 electrons, of which in this case carbon gets to form what we call covalent bonding, which is going to involve sharing of electrons. Okay, so how do we expect the sp2 to come out? So in this case, as we could talk about sp2, may have something like this, where you have a carbon maybe forming 3 different bonds. So it should be a double bond there and 2 single bonds there. So that may be oxygen there, then you have hydrogen atoms there. So that is sp2. So what does it mean? So it means 2 electrons are being shared with the oxygen atom, then 1 with an hydrogen atom. So the 4 are already distributed. Then as we get to talk about the first one, which is the sp hybridization, as you might guess, this basically is going to involve just 2 ways. So it may be that 2 double bonds. Then the other one maybe is going to have what? Triple bonds. A triple bond and a single bond. So something like this. So you may have triple bonds there and maybe a single bond there. So that is sp hybridization. So what you're going to have is you may have, so this one is an example of a carbon dioxide. Then in the other bond, we can talk about it being connected to the nitrogen and hydrogen atom. So these are the examples. These are the types of hybridization that carbon can undergo. All right. So now, why is this important? So this is very important for us to understand, and we need to basically understand how we get to differentiate these types of hybridization. Okay. So let's get into that. And just a tip on how to remember the type of hybridization. You just need to count the number of atoms to which a carbon is connected to. So by starting the first one, count the first one to be S, then the rest to be P. So in this case, for example, you can say that is S, then that is P. So it's sp hybridization. You can count that one S and P. Then the other one, you have S there, then you have P and P, which is giving us sp2 hybridization as well. Then this one you have S, then P, 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 sp3 hybridization. So we are going to just end at sp3 for the sake of carbon. But in a case where maybe you have, for the sake of other topics where you may have different compounds exceeding the three P's, you may end up going, you don't go to the sp4, you go now d sp3. So there's an introduction of a d orbital as you get to move, naming your hybridization. So let's get to talk about the types of hybridization more in detail on how they get to form as we get to look at our compounds there. Okay, let's get more. I'll start by looking at the sp3 hybridization. But before we get to understand what sp3 hybridization is all about, we basically need to understand the, the electron configuration of our carbon atom. So how do you come up with the electron configuration of carbon? So what you're going to have is, you basically know that carbon is something that is like this, carbon 6, and you have a 12 there, right? So if you come to write the electron configuration, what you're going to notice is that you have a 2 and a 4, knowing that the first energy level, or the first shell should have a maximum of 2 electrons. Then these other ones have got a maximum. The second one is a maximum of 8 electrons. So the 6 are already distributed. So by indicating the orbitals where you expect to find the electrons, you're going to have 1s2, 2s2, and then you get to have what? 2p2. So we're interested in these orbitals, the ones that are in the second energy level, representing the 4 electrons in the outermost shell. So let's get to show what we call the energy level diagram. Okay, so what do we have for our energy level diagram? So of course we are not interested in this, what is going to be down there, so I'll not get it. Okay, so I'll start from the 2s. So we have the 2s there. How many electrons are there? So you can clearly see that you have 2 electrons in the s orbit, in the second s orbit, right? There are 2. So we're going to show them there. So we have 2 electrons. Okay, so this is called an energy level diagram, telling basically the orbitals that we expect to have more energy. So what you need to understand is the p orbital and the s orbital in the same energy level, or in the same energy level, or maybe the same shell, have the same, don't have the same amount of energy. They differ in terms of energy. So you're going to see that the p orbitals are going to be slightly higher in terms of energy as compared to the s orbital of the same shell. Okay, so what is our 2p? So there's x, y, and z. How many electrons are they? We have 2. So we just have 1 there and 2 there. So 1 p orbital is empty there. So now, this is what we call our what? Our ground state energy level diagram. So ground state energy level diagram. Then this is what we call your ground state electron configuration. Very important to note that. So if they ask you to say, give us the ground state electron configuration of carbon, that is the way you're supposed to show it. So now, when carbon becomes excited, we'll change the term there, we'll put the excited state of carbon. When it's ready now to react or form bonds, take part in bond formation. What is going to happen is the electron that was on the 2s orbital there is going to be excited and go to the other one, to the other empty orbit. Okay, so what's going to happen? So you have an electron there. So the 4 different electrons have been distributed in the 4 different orbitals. So now, depending on the type of hybridization that we're talking about, so knowing that in this case, what we are talking about is we are talking about the sp3 hybridization, you need to count the number of p orbitals that are involved. Okay, but just before we get to do that, we also need to understand that we can also present what's called the excited state electron configuration, which tells us to say that, of course, the inner electrons we have in the first orbit, then in the second one now, instead of you showing 2 electrons on the s orbit, you're going to show a 1 there. So we have 1, and then you get to have 2p with now how many electrons? With 3 electrons. So this is what we call the excited state of what? The excited state electron configuration of our carbon atom. All right. So how would you present the sp3 hybridization? what you are told there, what it means is basically you have a combination of 3p orbitals with an s orbital. So you have s plus p plus p plus p, 3p orbitals. That's what you have. So you have 3 out of 4 of these are p, and if you multiply by 100, you are basically going to have a 75%. So you have 75% of p matter compared to s. So the hybridized or the hybrid orbitals that are going to be formed are going to be closer to what? To the p orbitals, because you have got more of the p orbitals compared to the s orbitals taking part in the hybrid formations. So these orbitals that are formed are said to be degenerate because they have the same energy. So we're going to draw them. How many are they? There are 4. So all these are going to combine because we have a combination of 3 p orbitals and the s orbitals. So they're all going to combine, and this is what we're going to have. So should be closer to the p, but should be lower. So we have 4 of them. Then each of them is coming with an electron. So now what you need to understand is, don't think maybe we have 3 p orbitals and a single s orbital. They get to mix up. So each of these orbitals is referred to as an sp3 hybridized orbital. A single one is sp3 hybrid orbital. It is not, you can't say you have sp and p, then you are wrong. So they are all called sp3. So we have 4 sp3 hybrid orbitals. Okay, so that's what we have there. So now these are the orbitals that are going to take part in bond formation. So in case of looking at methane, which is basically the natural gas, we said you have a common atom being connected to 4 hydrogen atoms. Okay, like that. So we said each hydrogen atom is coming with its own what? With its own electron. So basically, what's going to happen is there's going to be an overlap between the sp3 hybrid orbital and what? And the hydrogen sp orbital, because if you look at hydrogen, it has got an electron configuration of just 1. So it's just going to be like 1s1. So what is going to take part is the s orbital. So the s orbital is going to be overlapping with the sp3 hybridized orbitals. So you have 4 of them. So what is going to happen after overlapping now? So we can demonstrate that by drawing the orbitals. Okay. So just a quick recap on the orbitals that we have. So we have the s orbital. So we have the s orbital, which is basically spherical in shape, something coming out like that. Then apart from the s orbital, we also have what we call the p orbital. So the p orbital is something that is going to come out like this. Okay. Then you also have SPD, so you have the p orbital, which is going to be something like this. Something like that. Okay. So what is the way it is coming out? So these are the major orbitals that we're going to be talking about in this study. Okay. So now, the sp3 is a combination of the p with what? With the s. So what we have is our methane, all right? The Lewis structure, which is something like this. 4 different what? Bonds formed. That is sp3 hybridization. So how to get to draw that? So we get our carbon in the middle there. Then we can show that indeed there is sp3 orbital there. All right. So it should be 4. That. So now what is the overlapping with this now? There are 4 s orbitals, each representing an hydrogen atom. Yeah. So now these orbitals that are in red basically are the ones that are denoting the hybrid orbitals that we have formed. So each had an electron, if you can remember from what we had on our energy level diagrams. Okay. So now we said each hydrogen is also going to come with its own electron. There's that kind of an overlap there. So forming 4 different bonds. So these are the hydrogen atoms. There are 4. So that is how we get to draw these orbitals. So you've presented basically your methane using the structures there. Okay, let's now get to move to the sp2 hybridization. How is it different? So sp2, going back to our excited state of carbon, we said, of course, you are 2s initially, then you have 3p orbitals. So say 2p. Then what gets to happen is initially you add 2 electrons. Yeah. So now one is excited. Then these already add electrons. Yeah. So we've now presented our 4 electrons. We are showing them there. They are shown. Okay. So now what do we expect for sp2? So if you look at sp2, it tells us that it's a combination of an s orbital plus 2p orbitals. So we are only going to get 2p orbitals here, only 2, then 1 will remain. So this is what we're going to have. The s orbital is also going to go. So we have 3 sp2 orbitals. So all these are referred to as sp2 hybrid orbitals. So each is going to come with this 1 electron there. Okay. So that is what happens for sp2. So these are gone. That is gone. You've remained with one p orbital. So now think of it in this way. There is also another carbon on the other side. There may be another carbon on the other side, and it is also going to be in the same way. So implying that it has also remained with a 2p orbital with an electron, then it also has the sp2 hybrid orbitals. That's in case of where it is also sp2 hybridized. So we can imagine something like that. Then it also has its electrons like that. What basically is going to happen is that these are going to overlap and give us what? Give us what we call the sigma bonds. Then these are also going to overlap and give us the p of a pi bond. Okay. So now let's get to show what basically is happening here. Okay. So a very good example that you can look at is this kind of a case where there's a double bond between 2 carbon atoms, and then these carbon atoms are connected to 2 hydrogen atoms each. So if you look at each carbon, they are all sp2 hybridized. Yeah. So what you're going to say is you have your carbon there, then you have a carbon there. So these first of all should form a sigma bond between themselves, which is the overlapping of the hybrid orbitals that we had. Okay, each at 3 sp2 hybrid orbitals. So each at 3, implying that there should be another one there and another one there, making it what? Making them to be 3. And then this one should have the same 3 there. So that is the second one and the third one there. So all these are the sp2 hybrid orbitals, each adding 3 of them. So there should be an hydrogen there, an hydrogen there. So I'm just going by the Lewis structure. Okay, then even there should be 1 s orbital. Okay. So now the thing is, we add p orbitals. We add each carbon had a p orbital that was unoccupied. So we said our p orbital is something that can be drawn like this, right? So just put the carbon in between there, in the middle. So it's going to come out this way, something like that. Then I'll just show that just continue to the other side. Then even the other side will do the same. Then I'll show that it has continued down there. So that is our p orbitals that remained or that didn't take part in the hybrid formation. So we'll show some lines there. So this is what we call now a pi bond. All these other ones are referred to as the sigma bond. So whenever there's an overlapping of the orbitals, basically we say there is what? Sigma bond. So I'm showing the electrons that the hydrogen have brought in. Then I can now also show the electrons coming from the carbon atom, the 4. So there should be 1 there, 1 from each, giving us 2, 1 there, and 1 there. Okay. So there are 8 after combining 2 carbon atoms. So this is an example of what we're saying sp2 hybridization. So you've seen that there's an introduction of a new bond there, which is the pi bond. So how basically can we understand these bonds better? Let's get to look at the idea of what we're calling the sigma bonds and the pi bonds. So what you need to understand is that in each bond, I'll talk about the single bond there. Okay. So start with the single bond, then we can go to the double bond, then go to the triple bond, and we can go to even the 4 bonds. So double bond, triple bond, 1, 2, 3, 4. So in each bond there's what we call a sigma bond. So it's one sigma bond there. Okay. So it's one sigma there. There's also a sigma bond there which you can note that way as well. So all these are sigma bonds. So now for a pi bond, so here there's no pi bond. Here there's a pi bond. There are 2 pi bonds and 3 pi bonds. So basically what you need to understand that in each bond that is formed, it is a must that there's a sigma bond, which basically involves this kind of head-on collision where they get to mix up, they overlap like that. So that is like what you're saying, the sigma bond. In a case of the pi bond, basically this one doesn't involve the mixing up. Okay. So in each bond, there's only a sigma bond and the rest are pi bonds. Except in a case where you have a single bond, there are no pi bonds there. Okay, let's get to look at now sp hybridization. What basically gets to happen when you talk about sp hybridization? So we said an example of sp hybridization is a case where you can talk about a double bond in carbon dioxide, 2 double bonds in carbon dioxide. So you have your carbon there. So what gets to happen first of all, we can start from the energy level diagram, where you know in the excited state of carbon atom there's a single electron there. Then you have three what? 3 2p orbitals. Okay. So we can put now 3 electrons there. Of course, this is excited state carbon. This is our energy level diagram, which we can show this to show what we're trying to show the difference in energy between our orbitals there. Okay, so for this one, sp tells us to say that you have an s plus a p orbital, which means they're in the ratio of 1 to 1. So as you get to show your sp hybridized orbitals, they should be in between that part and this part, somewhere in between. So somewhere there. Okay. So we have 2 sp hybrid orbitals. Each is coming with an electron. So we can get one there and this one there. So if you mix up, we are going to have 2 sp hybrid orbitals, each with an electron. So this is basically what happens. It tells us to say that carbon which has basically undergone sp hybridization will just have sigma bonds, which is 1, 1. Then the other 2 are going to be pi bonds. So that kind of a carbon will have 2 pi bonds, implying that the pi bonds are these now that are going to take part using the p orbitals as well. So this is what basically happens under sp hybridization. So there are just 2 sp hybrid orbitals that are formed. Okay, let's get to see what is going to happen in terms of our drawing. How can we draw it? How best can we show it? So apart from this way, of course, we did talk about the case where you have a triple bond as well. It is also okay. You talk about a triple bond, and then you talk about a single bond one side. How is this going to happen? So it will happen the same way. So you have now what we're calling the sp hybrid orbitals as well. So there are still going to be 2 hybrid orbitals, telling us that there's a sigma bond there, and that one is a sigma bond. So except the double bonds or the 2 pi bonds are going to be connected to one atom rather than being connected to other atoms in a case of carbon dioxide. Okay, so let's just to show an example now. So in a case where you are talking about carbon dioxide, you have carbon there. So this carbon is, first of all, must form 2 sigma bonds with the oxygen atoms. So the oxygen atom as well, basically, if you get to study it, if you get to look at the structure, of the electron configuration of our oxygen, which has got 8 as the atomic number, you're going to see that you're going to have something like 1s2, 2s2, then 2p4, right? 2, sorry, 2, that is 2, 2, then that is, they're supposed to add up to, so it's going to be a 4, given 6 in the atmosphere. So that's what you have. So implying that what basically is going to take part in the bond formation, of course, if you look at the oxygen, which is taking part in the carbon dioxide, if you look at the Lewis structure, it's something that is like this: 2 double bonds to each oxygen atom. So the oxygen is not satisfied because there are 2 electrons there. So these are already forming 4. So it needs 4 more. So it has got 2 lone pair electrons there, like that. So the carbon is what? So it's 1, 2, 3. So it's sp. So 1. So it's sp. P. So it's sp2 hybridized. So what's going to happen is it's also going to form the same type of bonds. So there is our oxygen. Then it is also mixing up like that. Okay. Even the other side, you have the same. So the oxygen is there. So in the case of our double bond there, so we already have our sigma bonds there. So we have 2 sigma bonds already. These are now representing what we are saying the sp hybrid what? Orbitals that we have formed. So now what remains in this case is the matter of you now getting to show the pi bonds. Of course, we basically can remember that we had 2 unused p orbitals of what? The carbon atom. So we're going to show the first one. So the first one, I'll show it like that down. Then I can also show the other one, slanty. Then you can slant this side as well. Something like that. Okay. So I can show the slant one this side as well. Something like that. Then we can have the other one that is just uplight. That is for show it in white as well, so that we can validate what we're trying to show here. So don't mind the drawing, you can draw it better. Okay, so then I'll do this. Okay, so that is a pi bond connected to the oxygen on the left. Then the other one is going to be from this one to that other one there, like that. So that is also a pi bond. So what can you see? You can see that basically there are 2 pi bonds formed, and then you have 2 sigma bonds as well formed, showing you exactly where the 2 electrons, where the 4 electrons are taking part in bond formation. That is what we have. So this is in a case where carbon is forming double bonds. Now, what about the case where it gets to form a triple bond and then a single bond? What basically gets to happen in such a case? So it is something that is very interesting, basically. So you're going to have something like, so you have a carbon there, okay? Then this carbon, let's use this example where carbon is connected to maybe nitrogen and then connected to a hydrogen atom there. Okay. So straight away, knowing that it is sp hybridized, so it's going to form 2 sigma bonds, 1 and 2. So then the pi bonds, so there are 2p unused orbitals, which I'll indicate like that. Then another one. So that is just like, this is 1p orbital that we've shown there. Then I can show another one slanty, like that. Then it has continued the other side. So I've shown. Then on the other part, we expect to have the same for nitrogen atom, knowing that it is also sp hybridized. So our nitrogen is going to be there. Or I can even put a carbon there. It's fine. So it may be a case where there's a carbon like that and there's an hydrogen there. Okay. So we can have our carbon there. So this carbon again is also supposed to come with its own bond there. There's supposed to be a sigma bond formed. So like that, then the carbon is there. So this carbon has a p orbital that is remained unused. That then the other one should also be slanted, the same way that we've shown it on the first carbon. Then come out like that. Okay. So we've shown the p orbitals that are remained unused. So we can also show the other sp hybrid orbital of the other carbon there. So then at the tip we can have now the s orbitals for the hydrogen atoms at the end. So there are electrons there. Okay, so these are the sigma bonds that we have. So now the pi bonds, we can show them as well. So we have these connecting, then that one can also connect. So equally, the reflections as well should be in the same way. Okay. So this tells us to say that we have two pi bonds between the what? The hydrogen atom and then a sigma bond down there, telling us to say that there are three bonds formed between these two carbon atoms in this case. All right. So we've already shown this. So of course that is hydrogen and that is hydrogen. So we've basically demonstrated or shown how we get to present our different what? Our different bonds or sp3, or let me just say the different forms of hybridization that carbon can undergo as it gets to form different compounds that it does. Okay, so now let's get to move and basically understand the types of carbon atoms that we're going to meet under the study of organic chemistry. Okay, let me just create some space. Okay, so what is going to happen is this. As we get to look at organic chemistry, we can classify types of carbons in different ways. The types of carbon atoms, what we get to look at. So as we get to look at organic chemistry, we can classify our carbon atoms based on the number of other carbon atoms that are connected to them. Okay, so you have a carbon atom just connected to one carbon atom. What can you say in such a case? So this carbon may be connected to three hydrogen atoms. So because we know that each carbon should form a maximum of what? A maximum of 4. So in this case where the carbon is only connected to one other carbon atom, which is that one, it is referred to as what? A primary carbon. So a primary carbon is only connected to one other carbon atom. So we show it by a degree there. So a single 1 degree, telling us to say that that's a primary carbon connected to one other carbon atom. Okay, so this basically tells us where we are heading to now. So you may have another carbon atom connected to what? Connected to two different carbon atoms. So maybe you have another carbon atom there. In these other bonds, you may have hydrogen atoms. So in such a case, this carbon atom in between, which is connected to carbon atoms, can be shown as 2 degrees, as well as what? A secondary what? A secondary carbon. That's the way you get to look at it. Okay, so just an emphasis now, just one more thing. So these hydrogen atoms that are connected to such a carbon, which is secondary, are referred to as what? Are referred to as secondary hydrogen atoms. Okay, so this is a case where they try to say, whenever you see something like sec, like that, just know that what it means is the carbon involved there is a secondary one, is a secondary carbon. Of course, an example can be in a case where you have 3 bonds there, 3 bonds there. And then what you know is, since all these are single bonds, it basically implies that what you're talking about is an alkane, and an alkane with 3 carbon atoms is basically named to be what? Because they have male ethane, so it's propane. So you have propane there. Okay. So that is the way you get to present it. So now, let's get to move to the other one. So from secondary, it gets to go to what? So you now have a carbon atom that is connected to 3 different what? 3 other carbon atoms. So it will just be one hydrogen atom, and the rest will be what? The rest will be carbon atoms. It will just be one hydrogen atom. So you have 3 now. So this one is 3 degrees, and it can be referred to as what? A tertiary carbon. Okay. Tertiary carbon. So a tertiary carbon only is connected to a single what? A single hydrogen. A single hydrogen atom. Then finally, there may be another carbon that can be connected to four carbon atoms. So that is referred to as what? It is referred to as quaternary. So that is something that you're going to have, quaternary. So this one involves a carbon connected to 4 carbon atoms. Okay, so there are no quaternary hydrogen atoms because all the 4 bonds of our carbon atom are already used up in the bond formation. Okay. We can also classify our carbon atoms based on the idea of looking at the double bonds that you have. So in a case where you have 2 carbon atoms that have a double bond in between them, something like that. So you can classify these carbon atoms in 2 different ways. So you can think of the carbon atoms themselves that are taking part in the bond formation, in the double bond. So the carbon atoms that form a double bond are basically referred to as what? So are referred to as vinylic. So vinylic carbons are carbons that form a double bond in between them. So now we can also talk about the carbons that are attached to the vinylic carbons. So these other carbons that now comes immediately or attached or they are adjacent to the double bond. The carbon atoms that are part of a double bond, they are referred to as what? Allylic. So allylic carbons are basically carbons that are attached to vinylic carbons, where vinylic carbons are basically the ones that take part in the double bond formation. Okay, so in a case where they ask you to explain what allylic carbons are, basically they are carbons that are adjacent to a double bonded carbon atom. Okay, as you can see, these are adjacent to a double bonded carbon atom. So they are referred to as the allylic carbons. Okay, so now let's get to look at the different ways in which we can present our compounds. How do you get to present them? Presentation of our molecules. Okay, so with what we call the empirical formula, of which I know we are familiar with it. A very good example of an empirical formula is the case of this one. This is an empirical formula of what? Of glucose. So the actual glucose formula is this one. C6H12O6. So now you get to now go to the simplest ratio by dividing by the highest common factor into the moles there. It will reduce to that. So what does that tell us? So this tells us to say that an empirical formula basically is the simplest all number ratio. That is what it is all about. That is the one way in which you can present a formula. So now the actual one that is showing the exact number of atoms that you need to expect is what we refer to as now what? The molecular formula, which will basically show the chemical symbols and the number of atoms that you need to expect. Okay. So now apart from this molecular formula, we can also present our compounds. Of course, for example, let's say you're talking about maybe C2, then H, for example, CH5, C2H5, then maybe OH. So that is an example of the formula of one of our alcohols. So what is the molecular formula there? So you can now also look at it what we call structural formulas. So we have different structural formulas and we can basically get to see how we get to present them. So I'll use that very example for our alcohol where we have C2H5OH. How basically do we get to present our structural formulas? So under our structural formulas, we're going to talk about 4 different ones. So it's what we call the Lewis structure. So the Lewis structures of course may be presented in what we call the dot structures. So this will involve you to just like get to show each bond as 2 electrons. So of course you have we have 2 carbon atoms there. So knowing that, of course there's a single bond in between. So I can start with maybe a line bond structure to just help us understand how we're going to move. So I can start with a line bond structure. So structural formulas, we have what we call the line bond structure. Okay. So this is something that is going to be like this. You just join them. And I'm sure you're familiar with this. So then we know that each carbon should form 4 bonds. So 1, 2, 3, 4. 1, 2, 3, 4 already. Okay. So I'll start by putting the hydrogen atoms. 1, 2, 3, 4, 5. They're already done. So then we have an oxygen atom there, of course, being connected to an hydrogen atom there. So we've now shown what we are calling what? This is what we're referring to as what? The line bond structure. Of course, if you look at oxygen, it requires a total number of 8 electrons for it to be satisfied. So we need to show that indeed there are lone pairs there, of which we have 4. 1, 2, 3, 4, and 8. So it's balanced that way. So that is what we call a line bond structure. So this sometimes is also referred to as the Lewis structures in some textbooks. If you get to review some textbooks, it will show that as a Lewis structure. Okay, so you can also present your Lewis structure as what? As a dot what? As a dot structure, which is also one way of presenting a structural formula. By presenting these bonds that you're seeing as what? As the 2 electrons, because we said each bond basically tells you to say that there are 2 electrons there. So instead of you showing the lines, you can just show now the electrons. So just write it the way it is. Just copy it down the way it is. And basically now just put the electrons in between there. Okay. So how many electrons are they? So yeah, there's a single bond there. I'll put 2. Okay. So 2 electrons. You can use a different color there to just. So there are 2 there. There are 2 there. So yeah, there's also a single bond there. So I'll put 2. There I'll put 2. I'll put 2 here. I'll put 2 there. I'll put 2 there. 2 there. So basically, we are just showing now the electrons. That is what the Lewis or the dot structure is going to come out to present your bonds. Okay, so it implies in a case where maybe if you have a double bond there, it would imply you need to put 2 pairs of electrons like that. That's basically how you get to do it. Then apart from coming up with the Lewis structure, I'll leave the line bond structure there to just help us come up with what you're calling the condensed formula. So for the condensed formula, what basically gets to happen is you will just show them, except you only show the bonds between the carbon atoms and, let me just say, the main chain. You only show the bonds between the main chain. So you have carbon to oxygen. Then the rest are going to be what? The rest are going to be condensed. So if you look at the first carbon, it is connected to 3 hydrogen atoms. So I can show them there. Then the second carbon is connected to 2 hydrogen atoms. Then I can show them there. Then this is what we call now our condensed formula. You just basically don't have to show the separate chains. You just get to show the main what? The main chain. So this is called a condensed formula. Okay, so apart from a condensed formula, there's also what we call a skeletal structure, which is basically one of the important things that you get to understand as we get to look at this topic, because it's going to be very, very important and very much applicable, because in most of the structures that are going to give you, they are going to give you what we call the skeletal structure. So it's very, very much advisable for you to basically come up with a Lewis structure of dot forms, or basically of the line bonds, to just make it easier for you to simplify. So you have something like that. Okay. So use this very compound to demonstrate how we come up with what? How we come up with a line bond structure. So of course there's hydrogen there, hydrogen. So there are just 2 things that are very important as you come up with your skeletal structure. One is, don't show the carbon atoms. Don't show the carbon atoms. And don't show the hydrogen atoms attached to the carbon atoms. Okay. So now we are going to present the carbon atoms only. And we only get to present them by using a term. So in a case we are coming up with a line like this, if I draw something like that as my line or my skeletal structure, what it tells me is At the end, there is a carbon atom. So the meaning is there's a carbon atom there. There are two carbon atoms at the end. So that is enough as a skeletal structure. No need of you showing them. So now, in a case where you have three, you're going to have something like this. Draw a line and then bend again. So what it tells me is there's a carbon atom at every turn. Then and at the end, there should also be a carbon atom. So that is enough as your skeletal structure. No need of you showing the hydrogen atom. Just draw it as it is. In a case where you're talking about an alkane with maybe more, so maybe an addition, so you've added another carbon atom there. You can also add another one there. So in a case where maybe the carbon atom is maybe, for example, let's say connected to this second one, maybe you just connect a carbon atom. I can so just join it there to show that there's a carbon atom there. That is how you get to look at your presentation of the skeletal structures. So now, you don't only show carbon and hydrogen, but you get to show the other ones. So what I've said is don't show the carbon and the hydrogen atoms. Only show the hydrogen atom attached to what? To a different atom other than the carbon atom. So in this case, I have two carbon atoms, right? Okay, so I'll start by drawing a line like that. So what I know is there's already a carbon atom at start, then there's also a carbon atom there. So now there's an addition of an oxygen atom there. So I can indicate the bond down, going down, but I'll have to show the oxygen atom because if I don't show, it would mean that there's a carbon atom. So I have to show that there's an oxygen atom instead. So I'll put it there to show that there's no carbon. So whenever I show a different atom at 10, it implies that there's no carbon atom. Okay, so after that, I need to show the hydrogen atom that is attached to the oxygen. That is very, very important. So only show hydrogen if it is attached to an atom other than what? Other than the carbon. The carbon atoms and the hydrogen atoms will not be shown. You only get to show the hydrogen atom if it is attached to an atom other than the carbon atom. That is what is important as you get to look at your skeletal structures. Okay, so now some of you may be asking questions. What about the case where you get to have a carbon atom maybe with a double bond? How do you show it? Let's say it's a double bond there, something like that. And then maybe there are two single bonds there of hydrogen atoms. Or maybe I can even put, okay, we can start with that. Let's say there are hydrogen atoms there. How do you get to come up with your skeletal structure in such a case? How do you approach the question? So what you get to have is it's going to be something like this. So we only have two carbon atoms. So what I'll do, I just draw a line. Again, I'll draw another line. Okay. So whenever you do hydrogen, whenever you draw two lines like that, what it tells you is you have a structure like that. Okay. We can add something more there to just make it more interesting. What about if you get to add maybe another carbon there, and then maybe even a carbon going down, something like that, and then another carbon atom there. So how can you draw it? Of course, I'm trying to ignore the fact that there are hydrogen atoms there. So there are hydrogen atoms there. So you can show them if you want to. But I'm trying to focus more on the idea of you getting to come up with your skeletal structure. So your carbon atom is you have how many do you have? You have 1, 2, 3, 4. So I'll start counting. My starting point is the first carbon. So I have a second one at the end. I'll start from there again. I have my third one. And then I have the fourth one there. So how am I counting? So we have one carbon atom, 2, 3, 4. How many do we have? We have 1, 2, 3, 4 in the main chain. Then we have a sub one at carbon what? At carbon number 2. So I can also show it upwards. There's no harm to that. So I just connect it to the second one and show it go it up. Telling me that at the end there should also be what? There's also a carbon atom, which tells us to say that we have 1, 2, 3, 4, and 5. So that is enough to present that structure that we have on top there. That is how you get to present your structures. using the skeletal structures. And these are the different ways that you get to do in terms of presenting what? Presenting your structures. Okay. So basically, these are the things that you need to understand as you get to look at basic organic chemistry. So watch out for a video as we get to cover now the hydrocarbons basically, and also the reactions that they get to undergo. So thank you very much for taking your time to watch the video. See you next time. Enjoy your day.